and in your private, like what Ornov says, privately, and if you try to read it little bit with the references, probably you get it much better. I just try to give you just some steps, how things, how you can arrive, instead of exactly in this model what it is, like I can give you this flavor of that, and then I'll switch to some other problem, okay. So maybe which is interesting physically, and so which we are talking about here is just particles on a ring, and particles like 1 0 going to 0 1, okay. So the point is that you have a master equation M P equal to 0, that's a steady state master equation, okay. And let us say that what is P and what is M. So when you are writing M, right, some matrix, let us see, and then here you are writing all configurations, right, okay. So let us say that in the configuration somewhere you have the site 3 and 4, some 2 consecutive sites, okay. So there are a lot of configurations in this in this sequence. There are a lot of configurations where site number 3 and site number 4 are 1 and 0, the rest can be anything, so there are many places. So I am saying that there is a configuration here, the site number 3 and 4 are, let us say, this one, and this one is something else, I do not know what is that. So these are the configuration, and site number 3 4 is 1 0, the other ones are something like that, and some of them, some configurations has exactly at site number 3 4 this is 1 0, okay. So these are the place for site number 1 0, okay. So now if these are the configurations with site number 1 0, now you know that if you look at the corresponding from diagonal element here, with respect to this you have a minus sign, right, because this 1 0 will lose, okay. So this 1 0 will lose, and then exactly let us say that now name it, let us name it that this looks like that and like that, some configuration, okay. So there is exactly some other configuration somewhere else which is exactly same and like that, but here instead of 1 0 you have 0 1. I am just saying that this 1 0 has become 0 1, okay. So if you shift this configuration will appear, because this 1 0 becomes 0 1, everything remaining same. So what you have correspondingly, you have a in this diagonal place you have a minus 1, and for this one, because it will gain just below this, here you have a plus 1, right. This correspond to here off diagonal plus 1, because when this is losing it is going somewhere else, that's the way, okay. So the elements, what it says that it loses from the diagonal, gains on the column somewhere, okay. So that's the way the column sum has to be 0. So term wise, whatever you write here, A, B, C, there has to be minus A somewhere, okay. So that's the way they cancel, it's not only the sum, individually term by term they cancel. So what I am identifying is that these transition, this is occurring for site number 3 and 4, that's all which is happening with respect independent of what is the configuration. So this operation is given by but then there are many sites, of course there are many other sites where this is 1 0 and this one is 0 1, but there are other configurations where these 3 4 site is just 0 0 or 1 1, okay. So they are not doing anything, okay. So for those there is nothing is happening. So these elements I am just saying that so if it is 1 0, this is what I am representing schematically. So if it is 1 0, it is nothing happening, 0 0 nothing happens, 1. So that matrix would correspond to just this one, right. This is right, this is just 1 0. So wherever that is 1 0, that is minus 1, this is just corresponding 1 0. So I think I made a mistake, and that is probably a source of confusion. So H, if I write it in this basis, consecutive things is 1 0 or 0 1 or whatever. So I write 0 0 0 1 1 0 1 1, okay. So if I write like that, in 1 0 this is a minus sign, 1 0 in diagonal 1. So this is also the same basis, 0 0 0 1 1 0 1 1. So the diagonal will be here, right. This is my matrix. So the diagonal elements, here we have a minus 1, and this one will be some 0 1 will be appearing somewhere, you call it, right. 0 1 will be appearing here, okay, somewhere here, okay. So some column, like 0 1 will be appearing here and losing from here. So other elements are 0. So 0 0 0 0 are 0. So okay, 0 0 0 0 and 0 0 1 0. I think I'm not writing it proper, okay. So let me write it proper. So for 0, 0, everything is 0 because nothing is happening. For 0, 1, you can create a 0, 1 from 1, 0. You are putting it here, 1. You are creating here, this one, you are putting it here, okay? Because you are creating a 0, 1 out of a 1, 0, okay? So this is here. And so this is 0, 1 can never become, none of them can contribute to that. So that is 0. So 1, 0, you are only losing. So 0, 0 has no connection, You 1, 0, you are losing. So that's the 1, and 1, 1, nothing happens. Okay. So that's the matrix. Okay. So now probably it is clearer. Okay. So if you have other terms, let us say there is a back rate, then you have also accordingly you can write this matrix. Okay. So these are the terms which were, so whole master equation has these terms, and I am picking up only the terms which are related to two consecutive sides having 0, 1 or 1, 0. Okay. So this is the matrix which is doing that. So now this matrix times my, so my equation which I say that, this M I am writing is a operator summation over I, hi plus 1, and H as a operator, general operator, H is equivalent to that. And what I want a equation is that H operating on ED cross ED equal to 0. Okay. So you have to satisfy this equation. So now what I want to make it 0, just you directly put it 0, it will not, this is one way to solve the equation, right? I mean, other way to that it is not 0, but it is 0 if you sum. Under the sum it will be 0, because H operating on first two sides, next to side, you have to make a sum over all of them. So on the sum it will be 0. Okay. So you can make that happen. So what you can write, that is again answers, and that is what I am talking to, like a pairwise balance. Okay. So what you balance is that what is here is balancing with what is in the next two. Okay. So this is balancing with that one. This is the same kind of idea said little differently here. Okay. So it's just that. So what you do is that instead of writing that, you write an equation which is not 0 in the right hand side, and you write H times this equal to, not 0, this equal to, you think of some other matrix which you do not know at this stage, you introduce new things, but they are not dependent on the configuration, they are constant matrices. They are nothing to do some other matrices, but not related to your configuration, some constant matrices. Okay. So what you do is that this ED you replace by a constant, some constant basically, I mean the matrices which are not related to the configuration. So you replace it by ED, some other matrices which you do not know, cross ED minus ED cross ED. Okay. E and D still you do not know. Firstly, you did not know capital D, capital E. Okay. Now we are introducing two new more which also you do not know. Okay. So let us proceed and we will see that we will know them. Eventually we will know them. So now if you do that, but what is the use? What is the use is that you can see that this is like a reduction relation. You see, you have many D's in a system. In a configurations, you have, let us say, LDs, right? Somewhere one DE, this this is DE, EE or something, which is replaced by one E and another one which is not related to the configuration. Okay. So what you are relating is that the partition function or whatever, the probability of a system of size L to a system of size L minus 1 somehow. That's when you are doing a recursion. Okay. So these are words. If you do carefully, you get them like that. So basically, and what will happen is that you can see that these are constants. So the constant, so basically you have a sum where this term is constant and this is just reduced, and next one, this one becomes constant, next one, this one become constant. So but this negative sign which is coming ED here, it will, right, so this one will cancel with the next term. Okay. So under the sum, if you write it like that, under the sum they will cancel. Okay. So this is clear from here. I'm just saying that if you have DE, if you have a direct product DE cross DE cross DE like that, and somewhere you put this one ED minus that will cancel. Okay. So that part will just, under the sum it will cancel. Now what you get here, that will get from the other one, because it's, you have a trace also in the from other side. So it will be, it will cancel out. Okay. So what you get is the one of DE is replaced by ED. okay, but then it is just d, just one less with one ed. But then it will also produce a term which is -1 at the next side. But the next side will have a +1 and a -1. So it will keep cancelling. First one will cancel the next one and it will keep cancelling. So this one under the sum will cancel. Cancel this equation. So this will not h of this equal to 0, h of this equal to this, but this m of this, m times this direct product will be 0 because m has a sum. Okay? Probably, yeah, okay. Is it? Pair 1, yes. Next. One is next pair. But okay, you have got it. Yeah, okay. So because this one you are making constant, so this one remaining. But again, this is also there is a term where the previous one, this one remains, and this one is this is just forward one is a constant. Okay. So the next, so you can call it, right? I mean, this is I plus 1, I plus 1. The next one will be just I plus 1, di plus 1. Okay? That will keep cancelling. Okay, so that will just cancel. Okay, so under the sum, this term cancels, and then so your equation it becomes just that. So de is just, let me write it, ee ed. I'm just making this direct product, ee ed de dd. Okay, so this equal to this ee minus ee, and this is ee and ed minus ed minus de sorry, ed minus ed. Okay, and the next one is de, d times e, this times de minus de. Next one is dd minus dd minus d capital D, small d. Okay, so this is the equation you have to solve. Now there is a matrix, this equation you have to solve. So now try to solve the first one. So ee, this is basically nothing is 0, but that is anyway 0, right? E minus e. No, this is not 0 yet because e is still a matrix, right? You do not know, but you know that this is e has to be 0. Like if you multiply this side, this into that, so that will give you, this one will give you just 0, this times 0, and this one will give you just de, and this one will give you minus de. Okay, minus de, by the way, not ed, minus de, and then there is a dd. Okay, so you have an equation that
last term is
0.
0.
dd is 0. Okay, 0, 0. So now e, this one has to be 0. So this is you can see that if you take e as a scalar, right? I mean that is automatically satisfies, right? So now let us say that e, because these are choices which you introduce, any choice will work. So you make e equal to constant. So if you make e equal to constant, then this equation is satisfied. Okay, so let me put a red mark here. This one is satisfied, and also d equal to constant. If d equal to constant, then this equation is also satisfied because this equal to 0 anyway, dd minus d. Okay, so now you have an equation, only equation which is remain, that de equal to that. Okay, and this is the, I mean there could have been an inconsistency to start with, right? I mean because this is also de and this is minus de, so minus of that should have been that, and that is true. If it is a scalar, that is true. Okay, so these two equations gives you only one equation, de equal to de minus d small e. This is de, if you take a minus sign, did I make no, this is correspond to that, this correspond to this, sorry, de equal to that, d minus d equal to this. So if you take a minus sign, you just get this. This is the same equation. Okay, there is only one equation. These two equations are only one equation. Remember that here you could have come to an inconsistency. Okay, then you cannot proceed, right? I mean, so that is kind of consistently you are getting, but inconsistency how? It is possible that this, if you take e equal to scalar, of course this satisfy, but e equal to scalar would not make these two equations same or make inconsistent. So then e equal to scalar is not a solution. There can be another matrix E such that this is 0. E times this, E commutes with E has to be there. Are you getting this? E minus E. So they say that commutation of E times E equal to 0. And similarly this one equal to 0 means D times E has to be 0. These are the matrix equation. So D and E, if scalar, of course is naturally satisfied, but you could have some other matrix which satisfy this equation and still consistent with these two, right? I mean, in this case, these are scalar is fine with you. Okay, so this is a simpler one. So now the remaining equation is just ED, okay, minus D times ED minus E times, sorry, D times E, E times small d. Now I am writing in the sequence, this equal to DE. That is the equation. And now you still have choices, you make whatever choices you make. Okay. So you can make a choice, for example, D equal to minus 1, that's the, you can make a choice and whatever choice is fine. So you make D equal to, this minus sign you can get it, so put D equal to 1 and E equal to minus, D equal to minus 1 and E equal to 1, because there is nothing, now you are still free, all equations are satisfied, you are free, your, right, this master equation MP equal to 0 for any D and E now, which are scalars, okay. So you choose your accordingly. So you just make D equal to minus 1, D equal to minus 1 and E equal to 1. Okay. So this choice, so this becomes DE equal to D plus E. Okay. Okay. So now this is the equation which you have. Okay. So that's the general kind of equation. So this is what you say that all you start with you have a dynamics. And you have a master equation, and you write the master equation in terms of these operators, and what kind of equation they will satisfy, this DE will be given by this equation, where what you use here is a cancellation scheme which is like a pairwise balance. Whether it will work or not work, why it will work, details are not known, you try this, right? This is one kind of cancellation scheme. Okay. So this is one equation. So now I am just writing, so this is 1 0 goes to 0 1. And so now let us say that you have other rates. Okay. By the way, I pause for a moment here. So you have this is called an algebra, right? Sum of two matrices is same as product of two matrices. Okay, that's the only equation now. Now can you find representation? Right. So in this particular situation, you can find that because it is on a ring, it is the only equation. This can be satisfied by scalars also. Okay. Sum of two is same as their product. You can have choices, right? So that equation actually gives you a scalar, and that's a very simple equation. And so, and if it is a scalar, then you know that probability of every configuration is just d to the power number of particles and e to the power l minus n, and that is true, right? That is true, because this is just and all configurations is equally likely. This is a very simple problem, very simple solution. Okay. So now, if you make little more complicated, let us say this is P, and if you make it this side, it is Q, 0 1 to Q. Okay. And P can be thought as 1, right? One of the rate always you can set to be 1. Okay. So in this situation, the corresponding equation, what I get here, like the corresponding equation what I get here, DE equal to D plus E. If I have this one, now the equation will be DE minus QED equal to D plus E. Same procedure, you just put the matrices here, and this will be 0, this will write, this will be 0, and scalar still work. You just try doing that, right? So this will be the equation. Okay. So at this stage, I just wanted to say that these equations are very, for example, for when Q equal to 1, this is just a commutation, right? So for Q equal to 1, this is just a commutation relations, which is DE equal to D plus E. Okay. So this is the algebra. Okay. Whether there are matrices which satisfy this algebra, whether representation here, up to this you can come, and then you have to find representation. And I do not know whether there is a very generic procedure of finding representations. You have to try to some extent. I do not know. Here after that it depends on who, right? How much you are handling matrices. Right, so I do not know how. So this is DE equal to D plus E. That's a commutation relation you have. But all I wanted to remind you that you have already heard in previous talks by Arnav that if you have operators like A and A dagger, and if you know that among the commutation A equal to 0, A dagger equal to 0, A dagger equal to delta identity, these commutation relations are complete are complete in describing the systems, right? I mean, if you you can find the representation and this. So all I'm saying is that the model which I start with actually is given by some representation of given by some algebra. Okay, this is algebra. Okay, so whether you can find a representation or not, that's a separate task. But what kind of algebra they satisfy is this. Okay. So sometimes because dE minus QE d equal to d plus E, that's a commutation relation, people also define something called Q commutation. Okay, instead of, so that is basically dE minus QE d. This is exactly the definition of the Q commutation. Okay, so this is just this equation. Okay, so dE minus, that's the equation. Okay, so this is the problem on a ring. So I just wanted to tell you what will happen. I will not narrate this, but I will tell you what will happen to this problem. You just open up. Okay, so when you open up, open this, just 1 0 goes to 0 1 in the bulk, and then particle come here with rate alpha and goes here with rate beta. Okay, so that's your model. Okay, so you have a traffic, particle just goes, and this is just exactly the initial model we start with. So the equation which I wrote in the bulk, those equations will be anyway right, because everywhere, as long as you are doing this pairwise consecutive things, in the bulk the same dynamics is working. Okay, so the equations will be same. It is only that the boundary, right, the cancellation was, right, this one cancelling with this one cancelling with this one, so there will be some remaining term at the end which the boundary has to take care, right? Somehow smartly you have to convince the boundary that this has to be cancelled, and from the other side also two boundaries has to be cancelled. Okay, because if it is open one, the matrix product is just this side there is a vector v u, maybe v, and this side there is a vector w, right? So these vectors also you have to find out what these vectors are. Okay, and once you have these ones, in the bulk you have the same equation, dE equal to d plus E. This was there, this equation was there, and the scalar solution was working and everything is fine. Okay, so now what you have additionally is that this, because of this, you have one eigenvector. Let us say I think I can read it. So dW, particle goes out, so dW equal to 1 by beta W, and that another equation will come, this V will satisfy, that VE equal to 1 by alpha V. Okay, so this alpha beta, these rates will somehow adjust to the boundary ones. I am not deriving this, I am just saying that this will work like that. Okay, so these equations, now what are the conditions? The condition is that sum of two matrices is same as their product. Okay, and eigenvalues of D is, one eigenvalue has to be 1 by beta, one eigenvalue has to be one eigenvalue of D has to be 1 by beta, one eigenvalue of E has to be 1 by alpha. Okay, so if these are the only two conditions, right? And earlier you have a scalar solution, you would feel like this might be kind of pretty simple, how complicated this can be. Okay, so it turns out that the person who actually introduced it, Bernard Derrida, so it took him 6 months to realize that there is no solution to this problem, right? You cannot have a finite dimension, one can prove. The proof is simple, I am not giving it here. So we find out that if these are the equations, then you cannot find a finite dimensional matrix which satisfy these equations. Okay, it just becomes very complex. Just there is no matrices which satisfy this equation, finite dimensional matrices. Okay, except for some very simple scenario, like maybe alpha equal to 1 minus beta. Okay, okay, so some, except for very simple, some simple choice where you have a scalar solution, one particular case. For generally, if you put some alpha beta, it will not work. There is no finite dimensional representation we can find. And he actually found this representation of these matrices, infinite dimensional matrices, and the problem is solved. And this is one of the very celebrated solution. This is what you call matrix product answer. That's the starting point of this. Okay, matrix product answers. Okay, this is Derrida. and amino references I'm dead, I'm not remembering, but I know if you ask, I'll, after the talk I can tell you. So okay, so this is this is a method. But you can see that this is also based on a cancellation scheme, which is just cancelling something in the neighbor. Okay, so this is very similar to pairwise balance, and this equation doesn't have a solution, and solution doesn't have a finite dimensional matrix for solution. And there is a specific case when you say that alpha, when you want to enter particle, you know that there is a, if there is a 0, then only you can put a particle. If it is vacant, right? I mean, if it is vacant only, then you can put a particle. Okay, so so this is effectively, this will make a density as if so this, if it is 0, you are putting a particle with rate alpha. So this is effectively having a fictitious site here with density alpha. Then 1 0, right? I mean, if it is 0, put a particle with rate alpha. Okay, so instead of, if you say that there is a density here alpha, then you can see that if you have a particle here, you make a transfer. Okay, that is the same statement. So this side is a density, effective density alpha. This side, because it's a 0 density, is beta. Whole density is beta. So there will be particle density will be 1 minus beta. Okay, so when these densities are same, this is a simple problem, like alpha 1 minus beta equal to alpha. It is just an equilibrium kind of, both, it's a simple problem, just plot density. So that problem has a scalar solution like that. Okay, so the ring and alpha equal to 1 minus beta, and this is a kind of same problem. It's just a ring which is cut. It's an open system. Particles come and go. That average density is fixed. This is a non-conserved system. Okay, whose average density will be same as a conserved system with some fixed density. This equivalence would work when alpha equal to 1 minus beta. Okay. Otherwise, in general, the problem is pretty complicated, and to your surprise, I just wanted to tell you. I think this is again just to tell you, not that I'm calculating them. I mean, just saying that results of this, and which can be derived simply from mean field theory, right? I mean, this is the exact solution, good and great. But like in many things about Ising model, you can also know, right, phase transition. For example, on of today will do this mean field theory, right? When you want to do phase transition, a lot of things you can do just by simple arguments. So one can also argue about this. So I'll just tell the results. I will not argue simply or complicated way. No way. Okay. So the result is that if you have alpha and beta, so let us call it alpha. You have a beta. So okay, let me give you a little idea about what are the possible things can happen. Okay, so now particle going forward. Okay, then the point is that you have a current in this problem, right? I mean, you're just going forward, and a current carrying system. If you want to write an equation for density, that will be like a continuity equation: del rho by del t equal to del by del x of j, like Bustan sir must have written earlier. Like this is like biased diffusion. If you have a current, it's like a biased diffusion of particles, right? So you have an equation which is something like in this kind of scenario. If you have a current like that, because 1 0 going to 0 1, that is like something like del rho by del t equal to some del rho by del x plus some other terms, diffusion terms. Okay, so these ones, because this is kind of and these terms, and as you know, the second term is 1 by x square, del square by del x square. So this is 1 by L. There is a dimension here, 1 by L. Okay, so if this is present, then this is kind of not that relevant. Okay, so I'm just saying that if the particle is diffusing both ways, then the diffusion is the only thing which you see, because the mean is anyway 0. Okay, so if it is biased, if it is a biased diffusion, the important part is that it is moving. This peak is moving. Okay, so that's the most relevant part. Okay, and that part comes from the fact that del by del x, because there is a gradient, it's like moving along the gradient. Okay, so this is the equation. So it's a equation like that. The other term is less relevant. Okay, so this is like a first order equation. Okay, and then what you have is that you have two boundary conditions. This should have been solved by single boundary conditions. Okay, one boundary condition could fix it. But now you have a first order equation with two boundary conditions, and that's a mismatch, which is you have to satisfy this and satisfy that. How? So basically the system is kind of frustrated. It will satisfy only one at a time, right? I mean, in some scenario it will this one will win, Okay, one boundary will win. In some other scenario, some other boundary, the other boundary will win, and some scenario they will keep competing. Okay, so there are three different kind of phases you can have. Okay, so now what you have is that this side density is rho equal to effectively rho equal to alpha. This side density rho equal to 1 minus beta. Okay, so if this is wins, so what are you doing here? You are throwing particles here. Okay, so if it is alpha is very large, then you are throwing a lot of particles into the system. Okay, so it will be dominated by this boundary. If alpha is very large, it will be dominated by this boundary. If beta is very large, it will be dominated by this boundary. Okay, so I'm writing that. So there is so if alpha is very large, this side very large, this one here, so this is will be dominated by this boundary, and this is basically I call it high density because the density is very high, dominated by high density. And this one, beta is very high. Beta is very high means whole density is very high. That means particle density is low. So this is low density. Okay. And then this boundary, that there must be a phase between them, right? It cannot have let's say high density, low density, like that. Two things I find, this side, and then what you have is that there must be a, right? There must be a place where you go from this to the other. If you have two phases, there must be a phase boundary, right? And that's a, so you have a phase boundary somewhere here. Let us say somewhere here you have a phase boundary. Okay. Okay, you have a phase boundary, but you could expect that this will continue, but that is not true. Okay, what happens is that there are a region in the phase space where they keep competing. So there are two ways I say. If you put lot of particles, this side dominate. If you put lot of holes, this side dominate. What if you put both of particles and lot of holes together? Okay, so that's a very high beta, that is in this direction. High alpha, high beta. Okay, so in this region, it will be just half density because nobody will settle. Like I'm not hole like, I'm not particle like, right? So the density will be half. As many holes, as many particles. The system can accommodate as many holes, as many particles. Okay, and the density will remain half. Okay, so you have a phase here, which is where the density rho equal to half. Okay, here the density, high density, rho equal to alpha. Here rho equal to 1 minus alpha, 1 minus beta. Okay, because density is always 1 minus the whole. Okay, so that's the three phases, and the transitions are actually, these are kind of continuous transitions, and this is a discrete, it's a first order. Okay, so all these kind of complicated phases comes into the picture just to this simple problem. Okay, so this is very nicely described in that paper. So that's the point. So now if you want to calculate current vaguely, in a mean field way, if you want to look current, when do you find current? If you have a particle, and if particle in front of it, if you have a hole. If a particle finds a hole in front of it, then it will move. Rate is anyway 1. That's what is happening in bulk. Okay, so what is the probability of finding a particle? Rho. Here the density is not conserved, it is fluctuating, but average density here in anywhere here is just 1 minus beta. Okay, so if you change alpha, all along this is same rho, all along this is same rows because it's just 1 minus beta. Alpha it doesn't matter what is alpha. Okay, so you can put whatever density. So if density is this, current always is that if you have a particle and you have a hole in front of it, right? Vacancy. Having a particle is rho, having a hole in front of it is 1 minus rho. Right? So in a mean field way, if you think, it's just rho into 1 minus rho. That's the current. So the average current will be just, current is always anywhere J equal to rho into 1 minus rho. Okay, so here it is beta into 1 minus beta, here alpha into 1 minus alpha, and here it is 1/4. Okay, just the current. Just use this formula to get the current. So these are the three different phases, and they're separated by phase boundary. So this is a very nice problem, and this is the reference, and more I can tell you, right? I'll give you the more references later. I think that part is complete, right? I just kind of narrate how it get to things. Okay, at this stage, I think I have a right. I can take some questions, or some 20-30 minutes I can discuss another problem. Simple, much simpler. Okay, or I convert it into, right, that problem is simple enough to convert this class, at least the last one, into a tutorial. Okay, so I can ask you simple questions then, right, and then yes, there are other. Okay, so what is that, right? His question is that, well, very nice on the board and very nice, beautiful mathematics. Where do we use them? Okay, so there are many places. So question is that, where people actually have used them, not where you can use them. So one of the thing is that cell traffic. So for example, if you look at your cells, human cells or any other cell for that matter, the cell is somebody like that, and it should, minimum is that it has an identity. If you know a little bit of biology, then you know that this one, the surface of the cell is a polymer called actin polymers. Okay, so this gives you the rigidity that the cell can move wherever it goes. But then the point is that, and in the surface, how things enter into the cell is that there are a lot of pores at a lot of places, like water, iron, or all kind of things. Yeah, no, it's okay. 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 So now the cell has lot of holes. Okay, so pores, these are called pores, right? So things enter from there. But now most of the things are concentrated here. The DNA is concentrated in the nucleus. So anything which you want to transport, or for example proteins, when the whole life of a cell goes on making only proteins. That's all it does. Okay, so mostly large part of it. So this is only concentrated here. So let us say that you pop up a parasite. Something. So something, whatever things you want to send to the cells must enter here and go here. So how it is being carried is by some other polymers called microtubules. Okay, so there is a network of microtubules which actually are connected all over the cell, but they are also connected from the cell surface to this one. So how things are carried on these tracks called microtubules is by motor proteins. No, you ask a physical question, so I have to, right? I'm giving examples of really. So there are two different kind of motor proteins. Okay, it's not, so two, kinesin and dynein. So these motor proteins actually, if there is a track here, on the track, these are kind of, if you remember this cartoon, like they walk, like so there are two legs, and then it hold one leg and leave one leg like that, and after some time it hold it and put it this like, it just moves like, this is a cartoon picture how exactly it works. So what you can think, on a track, on a microtubule, how the molecular motors move is just a crowded environment, and there are a lot of them actually move primarily in one direction. Why one? You don't want to go out, primarily in this direction. Okay, so that's the way the transport occurs. So people actually find them. Okay, so experiments, many places people do it. In India also we do it. Okay, so what you do, I'm going away, but it's okay, I think. So what you do is that you take this microtubules. Okay, so you can you can elongate them on a surface. Okay, just on a surface. Okay, so on a glass plate you can put lot of microtubules, so they will make a road, big road. Okay, so now if you put motor proteins on the top of it, they are kind of aligned, and you have a lot of motor proteins which are going here, and they can actually, because of this one, they can actually try to compactify. Somewhere you can get, suddenly if you are putting a camera, they can actually coagulate in this kind of situation. They can come and just make at one place. So biologists are pretty smart. So what you do is that along with these motor proteins, you put some light signal. Okay, some fluorescence molecule. Okay, when you put your motor proteins, along with them you put some light signal. So if they are scattered, then you don't see much light, right? So if you were putting a camera, suddenly you find that like there is a big thing. So because somewhere they come close by and just kind of condensation occurs. Okay, so this is one example. I think I will stop there. Okay, this is one physical example. So there are a lot of such things which is modeled by this. Whether the model actually actually picks up all of it is not known. Okay, I can also tell you another one, the condensation part. the condensation part are also seen. So what happens is that, let us, so this is one of our work, earlier one. So this is, let us say, is a cell. Okay. So then and you know that all cells divide. Okay. So if you ask, if you go to biology, you try to ask what are the things, what makes the cell divide? How do the cell firstly know that it has to divide? Right? I mean, every cell is not dividing all the time. No, if you cut it for some reason, bad reason, then no, then they will fill it off. Okay. The neighboring cells will somehow know and then start dividing, fill it up. Okay, so they are not dividing all the time. So firstly, you can ask a lot of questions like how the cell know when to divide. Okay, now go to the next one. What is the story? The story is that the cell is here, and then after some time, when it wants to divide inside the cell, there is a nucleus they want to divide, and that will make two copies of the chromosome. And once the chromosomes are actually made into 2 copies, something happens also in the bulk, and all of the one which is giving the rigidity. Okay, they come together and they try to make a ring. They will make a ring here, like somewhere in the ring. And then this ring after some time starts shrinking, and eventually the cell divides. Okay. How do the cell know where is the center? Okay, how do the cell know that actually chromosomes are divided? You can ask loads of questions. Most of them doesn't have a good answer yet. Okay, so I'm just saying that one question is that once they form a ring, how do the contractile ring shrinks? Okay. Okay, I don't know whether it is useful. I mean, no. What do you think? Okay, now somebody has to stop me, otherwise I will just do it. Okay, so no, but I mean, I don't have an option. Okay, no, I'm just saying that so if what happens is that this is also another mechanism. So these actin polymers which are on the cell surface, which is gives you the rigidity to the cell, those are the molecules also which give you these muscles. Okay, so now my guide has come. He will guide me. So basically, these are the one. This is the actin polymers, which also give you the muscles. So what happens is that you think of so these polymers are actin polymers, and they are directional. So and the motor proteins which I talked about, they can work in one particular direction. And think of that this is directional, and the direction is towards whatever it's called here. No, some physical example. So, so what you do is that you have this actin polymers here, and some motor actually attached here. So what happens is that this motor has 2 legs. One is attached to this finger, and one is this finger. These are actin polymers. Then what happens is that this one starts walking this way. This one will start walking this way. So this, if you start like this, after some time it will just move. Okay, so this is the way the muscles contract. So now what you can do is that if you have a chain which is lot of microtubules, this is a system, and on which there are a lot of these actin polymers which are there, and each actin polymer you can think these are directional polymers, but of 3 units. Let us say 3 for convenience, 3 units. Okay, so what you can say is that when they are attached like that, so this is 1, 2, 3. So when it is attached, they are attached here. Okay, so this is the attachment. This is a motor protein which is attaching to actin polymers. So now what will happen is that after some time, this configuration, this will move here, this will move here. Okay, and they will become something like that. One is this one will go to that, and this one will come to that, and this motor protein is now here. This start working and it will go here. So this is the motor protein now. Okay, so this one will go here. Okay, so the dynamics of this system, you can, if you think it that each one has a center of mass, you can represent it as if this one, if there was a particle. So corresponding representation is that you have a particle here, and this one is here. Okay, so there are 2 particles, and then when they come together, they come to the 3rd side. Okay. So the dynamics of this system is that you have boxes, and randomly pick up 2 sides which are separated by 1, right? Randomly pick up a side and bring 2 particles from the neighbor and put it here with some rate. Okay, that's the dynamics. That's like kind of a zero range process which you talked about, and this kind of dynamics can actually give you condensation. So what happens is that on the cell surface, what you make a ring of actins, they automatically try to shrink, right? After and producing some kind of tension in the ring. Okay, so that's the way the cell shrinks and do this. So these are a lot of applications. 2 I have given. I will. No, please ask.
Molecular motors, you say, has something to do with stochastic ratchets. That is also part of stochastic.
Yeah. That is also stochastic dynamics. Yeah, this is modeling, right? I mean, how you model molecular motors, right? I mean, there is something that you have a phenomena and you have a model, and each model which you do, captures some part of the reality, not all, right? I mean, so this is when you think of condensation. I think ratchet is not something which will work. This one is better. Okay. I think any other questions? Okay, I think I will just ask simpler questions and try to write. Rest. Try to kill. No. I mean, I just let us think of another model. Okay, I just ask simpler questions and I built into models which you already know. Okay, so let us say that I ask you a question that if you write all numbers, listen to it. So if you write all numbers from 0 to 1000, okay, 0 to 999, okay, write binary representation of numbers from 0 to 1023. Okay, so you know why 1023. Write all numbers. Okay, so how many? And then each number has something like 10, 10, 110. Okay, so and then you say that anything, any number which has 2 consecutive zeros anywhere in this string, you just say that that's not allowed. Okay, a string with 2 consecutive zeros anywhere, that's no consecutive ones, because because there will be 0, or many of them are 0. So wherever, if you have 2 consecutive ones anywhere, you just that's not allowed. Okay, so now out of what is the number you have? That's the question. So you have total 1000, 0 to 1024 numbers. These are the numbers, and of which you want to strike out only those 2 numbers, right? I mean, keep only those numbers which do not have any consecutive ones anywhere. Okay, that's all you want to do. Consecutive ones, not zeros. I skip, change the question. Consecutive zeros is a little tricky here, because there will be a lot of, so consecutive zeros. The answer is same if you put a periodic one, but it's okay. So how to? I mean, I'm not saying that. Tell me 523, not that answer. I'm just saying that tell me how to do it. I mean, do you know how to do it? I'm saying that this question is related to Ising model some way.
Only 1 or 2 numbers will be there.
Huh?
Only total of
How many each number, can you tell me, anybody is not clear about the question? Question is clear, right? Write all the numbers. Okay, binary representation, all the numbers, and then so the question is how many, so this is 1023 or something, this is a 10-digit binary string, okay, 10-digit binary string, okay. So my question is that how many binary strings you have which do not contain any consecutive ones? How many, let me ask you a question, how many binary strings of size L has no consecutive zeros, consecutive ones anywhere? So basically, right, I mean, if you write one, next one you should not be 1, right? I mean, so those numbers you take out, and how many numbers will be left? That's the point. Okay. So this is what we want to solve, let us say, and I will try to say that what we study in Ising model is this one, some way. Okay. Okay. So we'll try to, I will try to answer this, but let us say that we try to answer this in a context of another statistical mechanism models, and I will define it. Okay. So I say that the model actually reduce to this question. Okay, so some way Ising model, but this question. This put is allowed now, right? Okay. Now, first I wanted to talk about the relevance, and maybe I can then calculate this. Can you think of how to calculate this? Yeah. Fibonacci. No, but so let us define a problem where these kind of things can come, okay? And then we see that, so what we define, the model is, let us say you have a ring, okay? So this is the L sides and periodic boundary condition, and then each side you have SI equal to 0 and 1, but your dynamics is that 1, 1, 0 going to 1, 0, 1. That's the dynamics. So a particle moves if and only if it is assisted by another particle, okay, from the left. Let us say, you can use also add the other one from the right. You can also add, which I'm not adding. It is assisted from the left, so you can also add 0, 1, 1 going to 1, 0, 1. That also you can add, but let us say that for simplicity I'm not using this dynamics, okay. This part is not there, okay. This one, only this. So what will happen to this system? Okay, so if you use, so now the density of the system is kind of fixed, right? You have a density of the system is fixed, right? Because you have just moving particle within the ring. So now if you start with some configuration, what will happen? What will happen for a given density, okay? So what will happen, for example, what will happen if the density is very low? No, the problem is clear. The particle can move only when they have a neighbor. To move you need one vacant place, that means one neighbor. In one dimension it is just one neighbor, okay. Particle can move if it has a neighbor. So if the density is low, what do you expect? No, nothing can move, more or less they are kind of separated, well separated, nobody can move, nobody has a neighbor. And if he has a neighbor, of course it will make one step and violate, right, violate this condition, right, that violate the condition that no, it doesn't have a neighbor anymore, right. You can have 1, 1, 0 somewhere, just remove because there are a lot of zeros. Okay. So if density less than, so what is the density that you can always get configurations which do not have neighbors? I'll ask the other way. Is there a density above which somebody or the other will have a neighbor? Half, okay? Because half is the density, maximally you can put like 1, no 1, 1, no 1, like that. And after that, doesn't matter where you want to put a particle, you will find a neighbor, okay? So so all configurations, right, anything, if the density is more than half, then it will, so if the density in this system, rho greater than half, okay, some particle or the other will have a neighbor, and the dynamics which I am talking about will keep doing shifting the particles, and so this kind of thing I call is the active one, active system, okay. This system remains active, okay. But rho less than half, you do not know what will happen, because you can have this, but it will appears like it will die out, okay. So I will not give the proof of this. So exactly there is a density rho star, rho c, which is half, okay. So above which this activity will survive, okay. So if you think of in this problem, I'm just giving you the results. If you want to find out what is this activity, okay. So if you can define activity, basically means that one surrounded by this kind of things, right. Whenever this, if you find this, you find that this is active. So you can think that 1, 1, 0 expectation value of that can be considered as a order parameter, because that, okay. And this for density, if you want to plot for density less than half, this is 0, and density above this you have some curve, okay. But this one, if the density is 1, of course you don't find them. So your argument, like if the density is 1, you don't find any of this, right. So basically that has to go to 0 also, okay. And this curve, this I call some activity order parameter, or phi. Let us call it phi the order parameter. So phi equal to 2 rho minus 1 times 1 minus rho divided by rho. Some, how I write it, I do not know. It will come back to this question, okay. So the point is, So if you are here, right, this will be the density and this is the curve which I draw. I mean, I'm not saying how. All I'm asking is that if you are here, right, so then the dynamics, look at the dynamics. So if you have 1 1 0 going to 1 0 1, okay, so then this one is moving, this is already here. So let us write this dynamics twice, okay. So because this side you do not know what, okay, so what I write is that I'll write 1 here, and next I write 1 1 0 0 going to 1 0 1 0, okay. So because all I'm saying is that this is the dynamics, of course, but what is the next side can be either 1 or 0. I mean, that's all can happen, okay. So now let us count what is happening in this dynamics. In these dynamics, you have, let us count how many consecutive ones are there, zeros are there, 1 0 is there. Just let us count only the consecutive ones, for example. So consecutive ones here is destroyed. Oh no, here is a consecutive one, that consecutive one is here, okay. So 0 1 also 0 1, so this is not changing, 0 0, so 1 1 and 0 0, nothing is happening. So let us look at this. There was 1 1 1 and 1 0 0, okay, and both of them are destroyed, right. I mean, so this second part tells you that both 1 1 and 0 zeros are destroyed. The first one said that they are insensitive to these two numbers, 1 1 and 0 0, okay. So now if you take any configuration initially, any configuration which have a lot of 1 1 and 0 0 in the system, right. So total number of 1 1 is n 1 1, total number of 0 0 is n 0 0, okay, n 1 1 and n 0 0, okay, these are the numbers, okay. So now so if you have, so let us say that n 1 1 is bigger than n 0 0, let us say. So you have a situation where n 1 1 is bigger than n 0 0, okay. If it, we will see what is that situation. In the your initial configuration, the consecutive ones are more in number than the consecutive zeros. That's what you start with. But then you use the dynamics for a long time. So what will happen is that this 1 1 and 0 0 will come somewhere, and then both of them will vanish, right. So let us say that so if it is bigger than that, each 0 0 will annihilate with 1 1, and finally some 1 1 will survive. 0 0 will go to 0. Because both 0 0 and 1 1 will be destroyed, right. You start in a box, right. You start in a box with some yellow and red balls are bigger, and each time you take a red ball and a blue ball, a red ball and a blue ball together and throw them. So of course the remaining ones will be blue balls only, right. I mean the one which is larger. So if n 1 1 is larger than n 0 0, then 0 0 will be 0, will not be there. So similarly other one, right. If n 0 0 greater than n 1 1, then 1 1s will not be there, okay. So can you say this one in terms of density? N 1 1 if greater than n 0 0, then you are sure that the density has to be greater than half, right. Can you prove that? Because n 1 1 n 0 0, because each bond can have either 0 0 or 0 1 or 1 0 or 1 1. So n 0 0 plus n 1 1 plus n 1 0 plus n 0 1, that has to be 0. Sorry, that has to be L. That has to be L. But at the same time, n 1 1, n 1. So basically, if you want to count how many ones are there, for each one, either in front of it there is a 0 or there is a 1, right. So if I call n 1 is the total number of ones, n 1 equal to just n 1 0 plus n 1 0 plus n 1 1, right. For each one, I mean I'm just saying this one has either a 0 or a 1 in front of it. So whenever you are counting a 1, if you count only places where in front of it there is a 0, places where in front of it is 1, you add them, this will be n 1. So now similarly, this is same as instead of this side, you can also call this side, right. I mean n 1 n 0 1 plus n 1 1, because this one now I am counting that for every one there is either a 0 or a 1 behind it. These equations are same. So basically n 1 0 has to be n 0 1 also, okay. So these are the equations, right. So this is one equation, n 0 1 equal to n 1 0, and if you use all them, and you can find that if you n11 number of 1 1 in the system is bigger than number of 0 0, then the density has to be greater than half. Okay, so this one is density greater than half. So in this situation, density greater than half, this zone, so that is 0 0 equal to 0, and this side 1 1 equal to 0. There will be no 1 1s here. Now let us look at this equation. If 0 0 equal to 0, then this dynamics is not there at all, right? I mean, in this side of the system, this dynamics cannot work, okay? Because 0 0 is not there. This one is still work, okay? But in this side of the system, right? I mean, so if I call it, this is A and this is B. So this side of the system, dynamics A is the only one which works eventually after a long time. And if you 1 1 is 0, then this is also not possible because it's not there. So neither of A and B work. Neither A nor B works. Okay, so that's the reason there is no dynamics eventually. It's inactive. So now let us look at this one. So what is this system? So now if you want to measure the configuration, right? You want to measure the configurations which has a given density and no consecutive zeros. Okay, given density and no consecutive zeros. If you want to find how many configurations are there, that's the question like that, right? I mean, if you have a system and there is another restriction, the density has to be this, but we will initially let us say that we do not want to restrict the density. Density can be anything, and ask this question in a simpler way and try to find them. Okay, so let us try calculating them, right? I mean, how do you do that? Okay, so I think that is very again useful in statistical mechanics, and so this is something which I want to do again. I think take it as a tutorial, okay, because these problems are simple. Okay, and these kind of transitions are generally these transitions where one side, it's not like a phase transition which we know in Ising model. The order parameter is going from 0 to non-zero, of course, but this side is a dead state. There is no dynamics. In Ising model, in a paramagnetic state, it's not that system is frozen, okay, that it's not doing anything. It's not like that. Here it is frozen. I mean, there is no dynamics. This is the active part. So this kind of transitions are called absorbing phase transitions, because the system here you are going to one state and you are dead forever. Okay. Okay. So let us try to find out this in a very basic way, and thereby we develop this concept of ensembles again. Yeah, we can put on a ring on open, right? I mean, maybe on a ring. Let us put a ring. Yeah. So now periodic boundary. How many binary strings? So I just use periodic binary strings. Okay, PBS. Okay, so I can say that periodic boundary string now onwards. Okay. So that's the question we want to answer. So let us do that. So now how do we do this? Is one way to do it just blunt. Like how do a kid does this? So you just say that write all them, find which are the ones. So you write the configurations 0 0. Let us do a small one 0 0 0 0 0 and 0 0 0 1 0 0 0 0 1 1 like that, and there are many, and then let this 1 1 1 1 1. Okay, so these are the configuration, and what you want to do is that for each configuration you have to say how many. Now instead of finding out no consecutive ones, let us say that try to find out how many consecutive ones are there on the right. I mean, so we want to count what is the average number of consecutive ones in these systems. So if you want to find that, so these all let us say all of them are equal weight, right? I mean, because when you count this, you give the same emphasis when you count that, right? I mean, so the probability of each of them is same. Okay, so that is kind of given. If nothing is said, that's the thing, right? I mean, if nothing is said, then all of them have the same weight. So now this one has number of consecutive ones 0. This one has number of consecutive ones 0. This one has number of consecutive one 1. So this is number of consecutive ones. So and this one has number 1, 2, 3, 4, and if it is periodic, it's 5. Okay, so this is 5. Okay, so this is the number of consecutive ones, and you want to make a sum and divide it by the number of configuration, right? I mean, make this sum, whatever the sum is called n11, and then what you find that your 1 average equal to n11 divided by total number of things we searched for, like 2 to the power whatever L. That's your number. That's the way to do it. So instead of doing that, we want to do it in some better way. Okay, what you do is that we want to put a counter. Okay, so what we want is that whenever we find this one, let's say there is a consecutive one is here is 1, I say that I'll write a x to the power 1 here. Okay, so if the number of consecutive is 3, I put it x to the power 3. Okay, so if it is 5, I put it x to the power 5. And instead of making this sum, I will make this sum. So what will happen? So this sum will give you summation over n x to the power n Cn. Some Cn, right? I mean, some wherever there is 1. And what can you now recognize what is Cn? Because if it is, x will not mix up with x square, right? So for each configuration, you have some x to the power some power you have put. Okay, if you put that, if you just add them, that coefficient of x to the power n is exactly the number of configuration which has 1 or n consecutive ones. Okay, so Cn, do you identify this? Anybody? Okay, so Cn is the Cn equal to number of configurations having exactly n 1 ones. Okay, that's Cn. So if you want to make this sum, can we make this sum? So if you call it gx, so this is just a generating function of Cn. Okay, what I do here is just a generating function of Cn. Okay, so can I calculate this? Okay, so another way of calculating this, right? I mean, so if I ask you how many configurations are, just this question if I ask you, it is very difficult to calculate, right? I mean, so this one itself is difficult to calculate. I go back to the previous one. If somebody asks you how many configurations have exactly 5 consecutive ones, that's the question if you ask. This is difficult to calculate, and we do this generating function. Okay, we reverse this problem. Okay, suppose somebody asks this question: how many configurations have n consecutive n 1 ones? Okay, if this is the question, the answer is Cn. You do not know how to find it. You generally write it as a generating function. Okay, so now usually what you have this generating function Cn x to the power n. Unless you know Cn, you cannot calculate this. Okay, so this one you are doing it. All you are doing it. So this one Cn x to the power n. So the number of configuration having n times this, right? I mean, so this is basically, I'm starting with this question now. Okay, question is that how many configurations have exactly n consecutive ones? Let's say this is the question somebody asks you in a binary string. So what you do is that this is Cn, and you write a generating function like that. Okay, so this generating function, this one Cn is just number of configurations, which is this. So which means that wherever such configuration occur, you just put x to the power n, right? So instead of doing this sum, you can call it sum over all configurations with x to the power number of n. I mean, this number of x, how do we write it? All configuration x to the power n, right? I mean, n is the n of that configuration. Okay, so that's what you are doing. Summation over all configuration x to the power n, because that's what I did here. For this configuration, you don't have to bother what it is, what n somebody want. Just for this one, you put x to the power 0. This one is to the power this. So it's just for each configuration, you are doing that. So that's the way you are actually coming out of this restriction. Here, we want to look for all configurations which is exactly n consecutive ones. This was the restriction which you could not do. When you write it like that, you are doing it sum over all configurations, and that restriction is gone. And for doing that, you are introducing this what you call fugacity, x to the power number of x to the power n of that configuration. N of this configuration is this one. N of configuration is this one. This is a configuration, and this is general name. This is configuration. This is n of configuration. So that's the way you are doing. Okay. So now can you do this? Can you do this sum? Okay. So now question is that n of C. how do I, is there a way to find this? You know, if it is a configuration, so if it's a general configuration SI, okay, what is n of C, n of SI? Is there a way to find it out? Can you tell me how you get this number in a simpler way? Not by looking at it. Is there a mathematical formula which will give you that? Summation over SI plus 1, okay? So if you write summation over SI plus 1, SI plus 1, then this will give 0, this will give 0. Whenever you have consecutive ones, you get 1, right? I mean, you know, so if for this one, this times that, will this time that, this time that, this time that, this time that, it will give you 5, okay? So this n of C equal to summation over I, SI plus 1, okay? So then the rest of the calculations I don't have to do, no? I mean, you know, I have done already in Ising model, because this one you can always fit it here, x to the power SI plus 1. X you can call it e to the power beta, okay? So that's the way, right? I mean, you know, this is something which is restricted. You can call it energy. N is your energy, right? I mean, you know, it doesn't matter. Something which is conserved, you break this conservation, you know, conservation and go to all configurations, and you correspondingly get this x. You can, if you write x is exponential something, that's a field. That's a field which corresponds to this n, okay? That's the field which tunes this, okay? So in other ways, you're just putting this x into the, you know, fugacities into the, you know, so the fugacities, the point which I wanted to make, the fugacities are those, right? On each configurations, you have something in mind, that's what I want to calculate. You are putting this x into the, right, I mean, they're counting exactly how many things are there, okay? So for example, in this picture, which I talked about, this D and E, okay, so there is a matrix D which represents 1, there is a matrix E which represents zeros, okay. But then if you sum of all configurations, of course the number of ones could be anything, but the models which I discussed, there I have to have a fixed number of particles, right, fixed number of particles. So what I do is that I don't keep track of number of particles, I will just put a fugacity to keep track of the particles. So instead of writing T, which is D plus E, if I write T equal to xd plus E, then what will happen, that this x to the power n, so let us write that. So T to the power L is now xd plus E to the power L, right. So if you, let us look at a configuration, right, I mean x to the power L, so this is xd plus E times xd plus E. So if you want to get x square, wherever there is a D, there is a x, okay. So if this, then it is x to the power that, okay. So this x is actually calculating that, okay. That's the way xd, if you put a x here, it will keep track of the number of particles, okay. Here, like here, it is keeping track of the number of particles, which is this. Along with this, let us say that you also want how many configurations are there which are n consecutive ones and exactly m ones, okay. So n consecutive, so C, let us call it C n m, okay. So that is the configurations which is exactly n one ones, n number of configurations which is n one ones and m ones, okay. So let us say this is the one. Then you put two of them, right? One tracks that, one tracks this, right? I mean, you know. So what is the corresponding thing will be here? Plus SI, plus, right? I mean, you know, n of SI is this. So x to the power this and y to the power summation over I SI, okay. Right? And if you write to e to the power beta and e to the power gamma or whatever, so you can call it e to the power beta. So this is, you can call it x. There is no harm in just writing x, because x anyway you do not know, you just put x to the power beta is the same one parameter, and y you can call it e to the power h or minus h or whatever, minus beta, e to the power minus h or h beta, because beta is anyway known, whatever, then this becomes just Ising model with a field, okay. So these fugacities, right, I mean, you know, this x and y in the generating function actually keeping track of the things, okay. So what is, so now look at your Hamiltonian in general, okay. So if you have some Hamiltonian h equal to e to, I mean not h, partition function equal to e to the power beta times something plus gamma times something plus alpha times something, whatever. So each one is like a field which is controlling this variable, keeping average, right, suitably fixing the average value of this. So if it is beta temperature, if you put E, then that means beta actually fixes this. That's the way. And gamma fixes, or H fixes summation over magnetization. Okay. So this is the way here, right? This Y fixes magnetization, X fixes energy. So that's and if you have more terms, you have more things. Okay. So now it is not very surprising, probably, right? To think maybe how Boltzmann could have thought about it, right? If you know generating function, probably you would have thought like that, right? Just right, if you want to count or fix energy, just for each configuration, you just put some X and let us keep track of it. And then once you have X, you have to bother about what to put this, how to do this sum. And of course, the sum is 0 to infinity. Then X has to be less than 1. Something less than 1 is e to the power minus beta. And of course, beta has to be one-sided and it's temperature. And that's the way you can, and it is a tuner. It's a natural tuner of energy. You can relate it to temperature. Maybe. I do not know. Okay, I think I stop here, and yeah, it's my last class. Right, I tried whatever I can, whatever I could do in non-equilibrium systems, but at the same time, I also tried to give some of the concept of statistical mechanics, which is right, very simple, but somehow it is not discussed, right? Not here, not right. Something which is simple, and it makes your understanding. I believe that this makes your understanding clearer. Okay, so with this I stop and ask for questions.
So let's first thank PK.
Okay. Okay. No, I'm a celebrity. Stand up. No, sorry. Sorry. No, sorry, man. No, but people are standing up. This is not that I. No, this is standing audition. Yeah, standing audition. Yeah, so that's the point.
Now you have to give us a party.
Outside. Okay. Okay, okay, I'll write it.
You can keep that.
Okay. Let me see if I can get one. Okay, I don't. You can get right. Directly you can get it now here from archive, but published paper I don't. You can find the reference from there. Okay, so the let me look at this. So this is, I've grown older, so now I cannot see. 0706 .1678. Okay, so this is archive. Archive this. This is matrix product answers. MPA. This is Blythe, na? Blythe, Evans. Blythe and Evans. Okay. Journal is J Physics A. J Physics A. But this is in archive. You can find this reference. This is for matrix product answers. And for zero range process, I think there is another article by Evans again. So that is Brazilian Journal of Physics. Okay, but then I'll put just archive reference, which is available to everybody. So this is 0501388. This is also by Haney and Evans. Okay, so this is another one. So a good, very good article of this one. That reference I don't. There is the I can find it, but I'll take some time. So go through this one, and you look at the reference by Derrida, 1994, right? So 94, 95. Yes, the 94, 95. Yeah. After we can find it here. Okay. So this problem is somewhere we studied at some point, so I don't want to emphasize that. So this is something which is studied as observing transition. This is the simplest part of it at sometimes in 2007, and yeah. Also this criteria at some point, yeah. Yeah, okay, any other questions? Okay then.
Thank you.